Hello everyone. Today I will present joint work with Sahasrajit and he is here with us today. So in this work, we develop a framework for extending the idea of matrix distortion to the setting where the voters may have some randomness in the way which they vote. So in this work, we consider single winner elections. So let's say there are n voters and m candidates. The voters submit rankings over all the candidates and the goal is to select a winner. There are of course many applications of this framework, the most popular one being the public choosing their representatives. And there are some emerging applications in AI. For example, if we need the feedback of multiple humans to train models, or if multiple models need to come up with a decision together, then they can use these voting rules to come up with a decision. So there are, of course, many voting rules, and different rules have different properties. There is no rule which satisfies all the desirable properties that we would like, but for different situations, we can choose our favorite rule. In this work, we will consider a framework for evaluating voting rules, which come from a spatial theory of voting, in which the assumption is that the voters and the candidates lie in a shared metric space, which is to say that their distances satisfy the triangular inequality. And the assumption is that the voters' cost from a candidate is their distance. And with our assumption is that the voters exactly know these distances and the submitted rankings are consistent with these costs. So this is the assumption which we will relax in this work. The goal of this framework is to find a candidate which minimizes the total cost, and the matrix distortion is the worst case ratio between the total cost of the outcome which is chosen by the voting rule versus the optimal candidate. This worst case is over all possible number of candidates and voters, and also the matrix space, that is the distance function, consistent with the triangular inequality. Some important works from matrix distortion which will set the context for our work. For example, Copeland has a distortion of 5. This is how Copeland works. For every pair of candidates, we consider their pairwise competition, and the candidate who wins the highest number of pairwise competitions is the Copeland winner. The Copeland winner may not always exist, and if there is a tie, then we can break that arbitrarily. The random dictator rule has a distortion of 3, in which we poll a randomly chosen voter for their favorite candidate. A very popular rule is plurality, in which we ask everyone for their favorite candidate, and the winner is the candidate who is the favorite for the highest number of voters. This is deployed in many settings, but it has a very high distortion which scales with m. Another important point is that any deterministic distortion, any deterministic voting rule cannot have a distortion better than random dictator. So I would also like to draw your attention to another literature on social choice, in which there are models to understand how voters may have some randomness in their perceived distances, and the utilities may be different under different models, and there is a lot of work on designing or understanding these utility models such that we can have an efficient inference of the best candidate. So this is how we combine these two literatures in our model. We have a distance function D, which is same as in the matrix distortion framework, and there's a distribution over the rankings which comes from the distance function. In this work, we work with the marginals that these distributions induce on the pairwise orders. So we are interested in the probability that a given voter I ranks candidate J over J prime. For example, in the Plackett-Luce model, which is a more complicated model, but for the purpose of these pairwise marginals, it results in a model in which these probabilities of voter I ranking J over J prime is a function of the ratio of distances. And we can parameterize this model by how much randomness we want in the model. For example, if this parameter theta is infinity, that corresponds to deterministic voting, that is with no randomness. And if we decrease theta, then that corresponds to more randomness. So now we can define the matrix distortion under probabilistic voting. So given a function Q, we will look at the worst case distribution which can induce this marginal. And for that worst case distribution, we will find the worst case expected cost of the chosen outcome versus the optimum outcome. So here the expectation is over two things. One is the distribution, the randomness in the votings, and also the randomness which potentially be in the voting pool. So we also want to characterize the set of marginals which make sense in the matrix distortion framework. That is, they are reasonable to study for distortion. One thing is scale freeness. So for the deterministic voting case, we have this very naturally that if we scale the space, then the distortion doesn't change. So we want this in our probabilistic voting model as well, that the marginals are invariant to scaling the space. And we also want that the marginal of voting between J and J prime is independent of the distances of the voter from every other candidate. And we want a monotonicity condition that if the distance of a candidate from a voter increases, then the probability of them voting for them is going to decrease. So these are our results. All our results are for the setting where there is a constant number of candidates and the number of voters is much larger than the number of candidates, which is a natural setting in most usual applications. So the distortion of probability continues to be linear in M, but if there is more randomness in the model, then it is smaller than the deterministic case. And for this, we provide matching upper and lower bounds. The interesting result is that for random dictator, if we have more randomness in the model, then the distortion can increase. Specifically for the Plackett-Luce model, it can, for example, for the case of theta is equal to 2, we'll have that the distortion can be scaling with the square root of the number of candidates. So this is to say that a random dictator is not so robust to the randomness in the voting of the voters. Whereas Copeland is much more robust to randomness in voting. And in fact, some amount of noise can help the distortion of Copeland. So this is because the adversary has a harder time to design a curated example for increasing the distortion. So specifically for the theta is equal to 2 case, the distortion is at most 2, which is lower than the constant of 5 that we see in the deterministic case. So this is one illustration of our results. So for Copeland, we plot the upper bound, and for random dictator, we plot the lower bounds. And the randomness decreases as we go towards the right. So further right is the case is converging towards the case of deterministic voting. So here, because we have an upper bound on Copeland, so it's not matching 5. But for random dictator, we can see that it converges to the value of 3, which we see in deterministic voting. But for more randomness, it is much higher than deterministic voting. It also scales at M. So this is we can see this from the 3 blue plots. For the case of plurality, it scales linearly with the number of candidates. So for let's say 12 candidates, it's between 11 and 23. And for the case of Copeland, we can see that if we have too much randomness, then that can also start to hurt, which is to say that like there is no more signal in the votes anymore. So finding a good matching bound for Copeland is an open problem. So in summary, we give a framework to include the randomness in the voters' behavior to the mated distortion framework. And we show that Copeland is robust to this randomness, whereas random dictator is not. And there are many potential extensions to this work. For example, we can do this analysis for more voting rules. We can close the gap for Copeland. And one more line of work could be to design more voting rules which are aware of the randomness in the voting behavior. So thank you so much. And do we have time for questions?
Yes, we do.
I was wondering if there's any relation between this and sort of the sample complexity of some of these rules. Like you could imagine a deterministic setting where you get a sample of the voters, and now you implement some scheme on it and measure distortion and see how, like, say, what is the variance and so on. In your case, you are assuming that the metric itself is sort of random. Is there a connection between these two models, or are they completely different?
I think it is completely different. Yeah.
The upper bound for Copeland went like above 5. Like presumably you can get something close to 5 for very large data, right? Like then you have to like once it's deterministic, it's 5, right?
Yeah.
So or do you actually think it's above 5 at some point? Is there any like?
Yeah, I would imagine it will be less than 5.
Okay.
Do you have any possibility results that are based on the randomness? Let's say if the randomness is so much, then your distortion, even with any randomized mechanism, has to be at least that much.
We don't have that result, but Yeah, that's a good point. It must not be very difficult.
With these random utility models, one thing you can often do is ask the same question several times to someone. And then you can even get an estimate of the probability, which will help with getting an estimate of distance. Have you thought about that?
Yeah, so we are assuming that like the voter has a noise in the way that they estimate the distance, and that will not change if we ask them again. Yeah, but like if we average it over like many different voters, then this is how Copeland gets an improved distortion, because like it is sort of taking everybody's voice into account as compared to random literature, which does not sort of average over.